So we have abstraction algebra, and abstraction algebra gives us a formal language to talk about the mathematical universe and operations and operators. And so it's really a calculus to work with this mathematical view. And now, how do we turn this into logic? Well, when we turn a calculus into logic, that can go really wrong. For example, as for Church's pure lambda calculus, which turned out to be inconsistent. And the reason why it turned out to be inconsistent is really because the pure lambda calculus, when you turn it into logic, it doesn't respect Cantor's theorem, right? It tries to equate mathematical objects and operations, and that is just not possible. So this led to Church's theory of simple types, and that's just the Tower of Universes idea. And we have seen that this idea is limiting. And fortunately, we don't have this limited view. And so we can turn abstraction algebra into logic in a quite straightforward way. And so the initial idea I had here in 2021 was based on the idea that any term is a formula. So there is really no difference between terms and formulas. And a theory is a signature together with a collection of axioms. And again, an axiom is just a term, so it's just a formula. And then models of such a theory are just algebras with that signature that have special value, a designated value true in them. And so that when I evaluate any axiom under any evaluation, then this will evaluate to this designated value true. And well, that's a really nice and nifty thing, and but there are a few problems with it. And so one problem is that if an axiom is just a term, then what about inference rules? All right, so every theory, every logic that is interesting has usually at least one or two inference rules. And if we only have axioms that are terms, what do we do with this? So initially, what I did is I just hard-coded the inference rules for implication, that is modus ponens, and the inference rule for universal quantification. I just hard-coded it into the logic, but there is a much better way to do this. So a second problem is, if we work just with a designated value, true, then this automatically divides all values into two classes, into two logical classes. Those values which are equal to true, there's just one of them, and all the others, which are unequal to true. And so this is really Boolean logic, right? What about non-Boolean logics, non-classical logics? What about them? And so finally, if we demand that all axioms evaluated true under all valuations, then we have no hope of achieving completeness for this logic because of Gödel's incompleteness theorem. All right, so that's why this initial idea has evolved in the past years. And where I'm at now is, I think, yeah, it's quite nice, and it feels like the right setting now. And so an axiom is not only just a term, but it's a sequent. I will say on a later slide what a sequent is, and what this leads to is that now inference rules are actually also just axioms. So we have no problem of having inference rules now as part of our axiomatic system. And instead of just considering one designated value true, we're considering a complete lattice of truth values. Okay, And yeah, so that's actually a very mainstream thing to do. I think on the first page of a book by Terence Tao, Compactness and Contradiction, he says that material implication A implies B. We can imagine it as meaning B is at least as true as A. So implication is really just a less than or equal relation. And we want this less than or equal relation to form an actual lattice, a complete lattice of truth values. And finally, we're not only considering all valuations, but we are also allowed to only consider valuations from a certain valuation space. And this is what at least gives us a chance at completeness. And so such a valuation space is just a subspace of all valuations, such that, well, it's not allowed to be empty. And if we have a valuation and we update a variable of arity 0 in this value, in this valuation, then the resulting valuation must again be a valuation of the valuation space. Okay, and if we have a valuation from the valuation space and a substitution, and then we form this valuation transformed by the substitution, then this valuation also must again be part of an element of the valuation space. So these are three simple conditions that a valuation space has to fulfill. And these are also all conditions a valuation space has to fulfill. Okay, so then this complete lattice of truth values, it forms a logical order of three components. The lattice itself, T, together with the relation less than or equal, and we also have a mapping from the mathematical universe to the space of truth values. And the idea is that any value of the mathematical universe can also be considered a truth value. And of course, if we already have a truth value, then this mapping that sends values to truth values, it's just the identity for those truth values. And so for two mathematical objects, U implies V is interpreted as the truth value of U is less than or equal to the truth value of V. So if we go a step further and say, okay, we don't want only a complete lattice, we also want it to fulfill the join infinite and meet infinite distributive laws, then what we obtain is a complete B-heighting algebra. Okay, and so the join infinite distributive law says just that we can distribute a meet over arbitrary joins, and the dual law states that we can distribute a join over arbitrary meets. And why is this interesting for us? Well, I'm later going to present various proof rules from the proof calculi for abstraction logic, and well, probably the two most important ones, or two very interesting ones, are cut-sac and cut-anti, and they need as a justification these laws, and that's why we're interested in complete B-heighting algebras. And this allows us, if we don't have these laws, then our proof calculi will form a sort of natural deduction. And if we allow these laws, then what we get is a fully symmetric sequent calculus. And so let's now first be clear about what is a sequent. A sequent in abstraction logic is a pair, L and R, where each of these components of the pair is a finite collection of templates. And well, this all what I'm saying also works with infinite collections. That's not a problem here. But you know, in a theorem prover can really only deal with finite collections. So that's what I'm focusing on for now. And so that's what a sequent is. And a rule is a special sequent where the second component is just a single term. So not even a general template, but just a term. And a formula is a rule where the first component of antecedents disappears completely. So that component is then empty. And now to state when is a sequent valid, right? To be able to state that, we need the notion of a truth range of a template. And that's just a generalization of evaluating a term with respect to evaluation and then forming its truth value. So the truth range of a template is we know that the template corresponds to an operation, right? Here, this operation comes from applying the valuation nu, and then we apply this operation just to all possible combinations of arguments from the mathematical universe and apply the truth value mapping to it. And so we get a collection of truth values here, and we call this the truth range of the template. And now it's easy to say what it means for a sequent to be valid. We just look at all the templates in the left component, and we form the union of all the truth ranges of that. And this gives us a big collection of truth values, and then we form the meat or the infimum of all of these values. And this is possible because we are in a complete lattice here, right? So that's why we can form this. And on the other hand, on the other side, we do the same thing. We form a union of all the truth ranges of all the templates in R, and we form then the supremum or join of this. Okay, and well, so then it's valued if the meat of this term here is less than or equal the join of this term here. And so that's a very that's a nice and neat definition. And here is basically the same again in a different layout. We have sequence, rules are special sequence, and formulas are special rules. And we can also write a sequent if we write all the templates S1 and Sn of the left component and all the templates T1 to Tm of the right component of the sequent. It's probably easier to visualize them just like this. We write the left components on top of an inference line, and we write the templates of the right component below the inference line. And then we can say that for evaluation nu, this template, this sequent is valid if this holds. So we form the union of the truth ranges of S1 to Sn. We apply the infimum or meet operation, and this must be less than or equal to the supremum or join of the union of the truth ranges of all the templates below the inference line. And so this becomes especially simple if all the templates involved are terms, all right? Because then we just take this evaluation here. Oh, actually, I think I forgot. We're not only evaluating it, but we also have to form the truth mapping here. So and here as well over all of these. But it's, I mean, that's easy enough. So and then we have on the left hand side we have disjunction, a conjunction, and on the right hand side we have a disjunction. And so this is really what we normally also think of in sequent calculus. Yeah, and if we have rules, then this becomes all a little bit simpler. Again, here I forgot the truth mapping around these values. And it becomes especially simple if we have a formula. If we have the truth mapping of this, then this has to evaluate just to true. And this comes because, well, if we form the meat of the empty set, then that's the top of the lattice, which is true. So this must be greater than or equal to true, or than just equal to true. Okay, so now we can say what is an abstraction logic, and we can also say what a model for such an abstraction logic is. And an abstraction logic is just a signature together with a collection of a collection A of sequence, and the elements of A are just called axioms. Okay, and a model of such a logic is now a triple, and so this triple consists of an abstraction algebra with the right signature, of course, and a logical order on the universe of this abstraction algebra, and a valuation space on the abstraction algebra. And for all valuations in the valuation space, every axiom must be valid for this valuation. Okay, so that's when we have a model. And to strengthen this a little bit further, if this logical order is not only based on a complete lattice but on a complete B-heighting algebra, then we call this a B-heighting model. Okay, so that's really all there is to it. And here's an example of a logic, and I call it a deduction logic with equality. And it has just 4 abstractions in its signature: true, implies, equals, and for all. And I've used here on the slide simple syntactic sugar for these abstractions, so that it looks familiar. And then we can see we have various axioms here about true, about how implication behaves, and how universal quantification behaves together with implication. And yeah, and here we have reflexivity of equality. And if we have 2 equal mathematical objects, then this means that you know, any and we have some property for this that is true for this mathematical object, then obviously it should also be true for the other object that is equal to it. And so these are just formulas as axioms, but we also have proper inference rules as axioms. Modus ponens is a simple one. So here we have A implies B and A, and from that we can follow B. And we have universal introduction, and this means, okay, if we have something where we know that A of x is true, and well, this here is now a template, right? So remember, like the truth, we define the truth range of a template. So when we write it like this, we're really considering the application of A to all possible values, and then we're forming semantically the infimum over it, right? And with this axiom, we're saying, okay, if we do this, then this must be less than or equal to applying the for all abstraction or operator to this operation. All right, and so here is an inference rule that I didn't have on my radar until 1 or 2 months ago. when actually Zarathustra, Elisa Brady, pointed out to me that this is missing. And he actually pointed out to me that I thought I had a completeness proof for this logic here, deduction logic with equality. But he pointed out that for each abstraction that has actually non-zero arity arguments, we need something so that we can say, okay, if the operations are the same, then the application of the abstraction to the operations must also be the same. And here we have one such axiom for the for all abstraction. Yeah, I will talk about completeness a little bit later in the conclusion as well. So I'm actually not sure that for this particular thing, for this particular logic, that this doesn't follow from all of these axioms. That might actually be the case, but probably not. All right. So now, the very interesting and nice thing about abstraction logic, I think, is that it unifies different views of logic, and in a very simplified way, I'm going to call these different views Hilbert versus Gensen. Okay. Or axioms versus inference rules, or semantics versus proof theory. And so proof theory doesn't really believe, or rather, you can do proof theory without referring to semantics at all. And if you do that, then proof theory is just a game of syntax with certain rules, devoid of any meaning. But that never really made any sense to me, and in abstraction logic we see that these two different sides of logic are rightly unified. And so what's a proof in abstraction logic? There are 4 different groups of proof rules. There are rules for assumption, there's a rule for substitution, there are weakening rules, and then the meaty part, there are inference rules. And all of these rules here are sound for all models. And these 2 rules here are sound for Behe-Heiting models only. And so let's go through these rules. Here is the axiom proof rule. If we have an axiom, then this is also just a theorem, right? That's why it's an axiom, because we want it to be a theorem. Similarly, assumption works by if we have certain things given, then of course as antecedents, then the succedents below the inference line, we can also just write them down here, but we have to make sure that we write down at least one, because the empty sequent denotes inconsistency. And then for substitution, that's also simple. If we have a theorem, then if we apply a substitution to each of the templates that appears in the theorem, then we get a new theorem. And because substitution is only defined modulo alpha equivalence, this here gives you also the rule for alpha equivalence. Then weakening. There are various forms of weakening. You can add, if you have a theorem, you can add an arbitrary template above the inference line or below the inference line, and you get, again, valid theorems. There are weakening rules for binders of templates. And, well, if you have a template then you can throw away those binders that do not occur free in T, right? And you can add arbitrary other binders. So if you do that, you go from a valid you go from a theorem to another theorem. And the dual rule to this is you can do the same also below the inference line. And now the interesting rules for inference, like for infer and cut. Let's start with this rule. What you can do is if you have two theorems and one conclusion or succeedant here cancels itself out with a premise or an antecedent in the other sequent, the other theorem. So this cancels each other out as long as none of these variables occurs as a free variable in any of the t's here. Okay, and so you can just cancel this out, and then you get a new theorem here, from which C and C with various binders has been cancelled away. And because these rules are symmetric, you can do the same below, like with, you can just change what's above and what's below the line, and you again get a valid proof rule. And so now cut proof rules are generalizations of infer proof rules. And what is more general here is that you can cancel the C with the C with potential binders, also in the presence of additional succedents here, or antecedents in this case. Yeah, so canceling also works in these circumstances, and you get a new theorem here where the C doesn't occur anymore. Yeah, so these are all of the proof rules. And with these proof rules we can form two proof calculi. I'm calling one of them natural deduction, and the other one I'm calling sequent calculus, because, well, there are like obvious generalizations of what we normally understand under these terms. And so natural deduction for abstraction logic is a calculus where we are only dealing now with rules, not with general sequence. So in the bottom we will always have just one term instead of several templates under the inference line. And well, this calculus is sound for all models, so where the logical orders are complete lattices. And it consists of these proof rules. Axiom, assume, and subst appear in both calculi that I'm presenting. And of the other rules, the cut rules are not valid here for natural deduction, but only the infer rules. And because we only have terms under the inference line, really the only rules that are interesting to us here in the natural deduction calculus are the anti-rules. All the other rules are not interesting to us. So the other calculus is the sequent calculus, and it's fully symmetric. So what you can do above the inference line, you can also do below the inference line. And this calculus is sound for B-heighting models. And it consists again of axiom, assume, and substitution. It consists of all the add and bind rules, add anti and add suck, bind anti and bind suck. And it also has the two cut rules, cut anti and cut suck, as part of its calculus. And of course you can also use infer anti and infer suck, because cut anti and cut suck are just generalizations of these rules. And so now I think Here we see clearly that abstraction logic unifies these different views of proof theory and semantic, because well, natural reduction and sequence calculus have really been developed by Gensen as poster childs for proof theory, right? But here in abstraction logic, there are also calculi that are really just Hilbert-style axiomatic systems. And so if we extrapolate a little bit further from this, then we can say that abstraction logic, it is a logic because it just has, it has axioms, it has the semantics, but it's also a logical framework because you can state all sorts of inference rules in it. Yeah, so the same as you do in a logical framework, but it's also logic. So this has really, these are not just rules, they have a meaning. All right, so that's basically it. All of this you can find in more detail in the book, in the draft of the book that's available on abstractionlogic.com.